The number of signals in a proton NMR spectrum indicates the number of different kinds of protons in a compound. And what we mean by different kinds of protons are protons that are in different electronic environments. So identical protons or protons that are in identical electronic environments are what we call chemically equivalent. And such protons, the chemically equivalent protons, fall into two categories. They can be either homotopic or enantiotopic. We define homotopic protons as such that if a molecule has an axis of rotational symmetry that allows one proton to be rotated onto the other without changing the molecule, the protons are said to be homotopic. So if I take a look at this molecule here, you can see that there's an axis that runs down the molecule that if I was to rotate that 180 degrees, I would end up swapping these two protons. So one proton can be rotated onto the other without changing the molecule. Therefore, these two protons are homotopic. The same thing applies with this molecule here, which has an axis down the middle like this. Again, if I was to rotate this 180 degrees, I would swap these two protons, but there would be no change in the molecule. Therefore, these protons are homotopic. The same thing applies to the two protons that are shown in cyclopropane. Another simple test to determine whether protons are homotopic or not is to replace the protons one at a time with another atom. So if we take this molecule here on the left, and if we replace each one of the hydrogen atoms with a deuterium atom, and we end up with the same compound, well, then the protons must be homotopic. This is a really fast and accurate way to determine if protons are homotopic if you're unsure about the axis of rotation. If you're unsure about the plane of reflectional symmetry, well, the good news is that the replacement test is universal. So it's going to work to identify any equivalent protons, whether they are homotopic or enantiotopic. So if I replace both of the hydrogens in this molecule with a different element, so they're being replaced with deuterium here, and if I end up with two molecules that are enantiomers, then the two protons are enantiotopic. This decision tree helps us to decide whether protons are chemically equivalent or not chemically equivalent. Furthermore, it can help us decide when chemically equivalent protons are enantiotopic or homotopic. So first, to determine if protons are equivalent, we'll look for a rotational axis of symmetry. If we have that, the protons are homotopic. If none is found, then we'll look for a plane of symmetry. If there is a plane of symmetry, then the protons are enantiotopic. If neither of these apply, then the protons are simply not chemically equivalent. If two protons are neither homotopic nor enantiotopic, then they are not chemically equivalent. If you try the replacement test and you end up with diastereomers, the protons are called diastereotopic, and again, they are not chemically equivalent. If you take a look at this molecule here, and if you do the replacement test to both of the protons highlighted in red, and you end up with a pair of diastereomers, they are diastereotopic. Again, if the protons aren't homotopic nor enantiotopic, then they are not chemically equivalent. If you take a look at the two protons here in R2-butanol, these two protons can't be interchanged by rotational symmetry or reflectional symmetry. You could try doing the replacement test and you would see that what you end up with are diastereomers. Luckily, there are some shortcuts that you can take to help you identify how many signals you should see in a proton NMR spectrum. First of all, the two protons in a methylene group will be equivalent if there are no chirality centers in the molecule. That's exemplified by this molecule here. These two protons, highlighted in the green box, are chemically equivalent because there are no stereocenters in the molecule. Secondly, the two protons in a methylene group will not be chemically equivalent if there is a chirality center in the molecule. So in the molecule on the right, the two protons highlighted in the green box are not chemically equivalent. And the reason why is because there is a stereocenter in the molecule. Another quick rule is that the three protons on any methyl group will always be equivalent to each other. So anytime you see a CH3 group, you know that all three of those protons are chemically equivalent. Multiple protons are equivalent if they can be interchanged through either a rotation or a mirror plane. You can see clearly that there's a plane going down the middle of this molecule. Therefore, these 4 protons highlighted in green are chemically equivalent. Also, the 6 protons in the 2 methyl groups at the ends of the molecule are also chemically equivalent based on the rotational axis. You might remember that in cyclohexane we have a total of 12 protons. 6 of them are equatorial and 6 of them are axial. The axial and equatorial protons are in different electronic environments. So technically there are 2 types of protons in cyclohexane, but what we see is only one signal is observed in the proton NMR spectrum. And there's a good explanation for that. What happens with cyclohexane is that at room temperature, the chair interconverts rapidly between these 2 conformations. The NMR isn't fast enough to capture these 2 individual structures, so what we see is an average of the 2. It's like a blurred photo in a way. If we were to run an NMR on cyclohexane at minus 100 degrees Celsius, we would see a difference between the axial and equatorial protons, and that's because at minus 100 degrees Celsius, the ring flipping would be so slow that we could observe the 2 signals.